In number theory, an algebraic integer is a complex number that is a root of some monic polynomial with coefficients in Z. The set of all algebraic integers is closed under addition and multiplication and therefore is a subring of complex numbers denoted by A. The ring A is the integral closure of regular integers Z and complex numbers. The ring of integers of a number field K, denoted by OK, is the intersection of K and A. It can also be characterized as the maximal order of the field K. Each algebraic integer belongs to the ring of integers of some number field. A number X is an algebraic integer if and only if the ring Z, X, is finitely generated as an abelian group, which is to say, as a Z module. Definitions. The following are equivalent definitions of an algebraic integer. Let K be a number field, in other words, for some algebraic number by the primitive element theorem, is an algebraic integer if there exists a monic polynomial such that, is an algebraic integer if the minimal monic polynomial of over is in, is an algebraic integer if is a finitely generated module, is an algebraic integer if there exists a finitely generated submodule such that. Algebraic integers are a special case of integral elements of a ring extension. In particular, an algebraic integer is an integral element of a finite extension. Examples. The only algebraic integers which are found in the set of rational numbers are the integers. In other words, the intersection of Q and A is exactly Z. The rational number a, b is not an algebraic integer unless b divides a. Note that the leading coefficient of the polynomial bx minus a is the integer b. As another special case, the square root n of a non-negative integer n is an algebraic integer, and so is a rational unless n is a perfect square. If d is a square-free integer, then the extension k equals q is a quadratic field of rational numbers. The ring of algebraic integers OK contains square root d since this is a root of the monic polynomial x2 minus d. Moreover, if d1 the element 2 is also an algebraic integer, it satisfies the polynomial x2 minus x plus 4 where the constant term 4 is an integer. The full ring of integers is generated by square root d or 2 respectively. See quadratic integers for more. The ring of integers of the field has the following integral basis, writing for two square-free coprime integers h and k. If zeta n is a primitive nth root of unity, then the ring of integers of the cyclotomic field Q is precisely z zeta n. If alpha is an algebraic integer, then is another algebraic integer. A polynomial for beta is obtained by substituting xn in the polynomial for alpha. Non-example. If p is a primitive polynomial which has integer coefficients but is not monic, and p is irreducible over q, then none of the roots of p are algebraic integers. Facts. The sum, difference and product of two algebraic integers is an algebraic integer. In general, their quotient is not. The monic polynomial involved is generally of higher degree than those of the original algebraic integers, and can be found by taking resultants and factoring. For example, if x2 minus x minus 1 equals 0, y3 minus y minus 1 equals 0 and z equals xy, then eliminating x and y from z minus xy and the polynomial satisfied by x and y using the resultant gives z6 minus 3z4 minus 4z3 plus z2 plus z minus 1, which is irreducible, and is the monic polynomial satisfied by the product. Any number constructible out of the integers with roots, addition, and multiplication is therefore an algebraic integer, but not all algebraic integers are circumstructible. In a naive sense, most roots of irreducible quintics are not. This is the Abel-Ruffini theorem. Every root of a monic polynomial whose coefficients are algebraic integers is itself an algebraic integer. In other words, the algebraic integers form a ring which is integrally closed in any of its extensions. The ring of algebraic integers is a Bezout domain, as a consequence of the principal ideal theorem.